Today we'll be talking about Bayes' theorem, the meaning, the proof, and the applications. The agenda for today is that we'll first talk about what Bayes' theorem actually states, how to prove it, and its applications for the real world in the cases of drug testing and finding beetles.
Basically, Bayes' theorem states how a subjective degree of belief should rationally change to account for evidence. For example, there's a certain probability that you have a cold. If you're coughing, the likelihood that you have a cold is much higher. And Bayes' theorem states how to adjust the probability that you have a cold, given the fact that you are coughing. Bayes' theorem is stated at the bottom of the slide. P of A bar B just means the probability that event A will happen given that event B happened, or the probability of A given B. The probability of A is known as a prior, or the probability of A without taking into account any evidence. The probability of A given B is known as a posterior, or the probability of A given that B happened. A is a hypothesis, which is the event being looked at, say whether or not you're sick, and B is the evidence, which is that you're coughing. Looking again at the equation, the probability of B given A, or the evidence given the hypothesis, is the probability that the event B would occur if the hypothesis A was true. So the probability that you'd be coughing if you had a cold is pretty high. That quantity over the probability of the evidence gives the support that the evidence B provides for the hypothesis A. Calculating the probability of the evidence or the probability of B is a bit strange. If there are multiple hypotheses, the probability of B is the probability of B given that the first hypothesis is true times the probability of the first hypothesis, added to the same for the second hypothesis, and so on until you reach your number of hypotheses. If there's only one hypothesis, say that a coin turns up heads, then you would calculate the probability of B using two hypotheses. The first is a hypothesis that the coin turns up heads, and the second is a hypothesis that the coin turns up tails. To prove Bayes' theorem, we first need to consider A and BK, which are sets. The probability of the intersection of the two is the probability of A times the probability of BK given A, as well as the probability of B times the probability of A given BK. This is true because intersection is commutative. Then we can say that the probability of the intersection of A and BK is the probability of BK times the probability of A given BK over the probability of A, which is beginning to look a lot like Bayes' theorem. To prove that the probability of B, or the probability of the evidence, is equal to the probability of B given the hypothesis 1 is true, times the probability of hypothesis 1 plus the same for hypothesis 2, and so on, we first say that S is equal to the union of all AIs, where AI is an event in S, and no two events share elements, which is what the second part of the top line means. Then we can say that A equals a union of A and S, and we know that S is a union of all AIs. And from there, we can move the iterative union outside and say that A equals a union from I equals 1 to n of the intersection of A and AI. Then we can take the probability of both sides, and because probabilities add, we can move the iterative union outside and change it to a summation, so that the probability of A is a summation from I equals 1 to n of the probability of the intersection of A and AI. Then we can say that the probability of the intersection of A and AI equals the probability of AI times the probability of A given AI. And then, when we're all done, we can say that the probability of A is the summation from I equals 1 to n of the probability of AI times the probability of A given AI. This is a bit confusing here because A is the evidence and AI is a hypothesis. So now we can fit this new part into what we had from the last slide to get Bayes' theorem, which is that the probability that the hypothesis AI is true given evidence A equals the probability of AI times the probability of A given AI over the summation from j equals 1 to n of the probability of AJ times the probability of A given AJ.
Now we'll see how Bayes' theorem works with real-life applications. For drug testing, Bayes' theorem helps us see how accurate the tests are. Let's say the percent of people who use a certain drug is 0.5% of the population. The test in question tests positive 99% of the time given the person is a user, and tests negative 99% of the time given the person is a non-user. With these probabilities, what is the probability that a person who tests positive is actually a user? This would be probability of user given positive test, or the probability of U given P. First, we write out the formula for Bayes' theorem for the probability of U given P. Then we plug in the respective values as given in the explanation slide. We've seen before that the probability of a person being a user is 0.5%, and the probability of a positive test given a person is a user is 99%. So after we find that the probability that a person is a user given a positive test is actually 33.2%. Clearly, this test is not very accurate because in the event of a positive test, it is far more likely, by 66.8%, that the person is not a user. So after using Bayes' theorem, we realize that this test must actually be far more accurate if we are actually to use this in the real world. We can also use Bayes' theorem when trying to determine the probability of a beetle that we have found is of a rare species. Let's say that there are two species of beetles. They are either rare or normal. 0.1% of all beetles are either of the rare species, or 99.9% of the beetles are of the normal species. Furthermore, of all the beetles, there are two types of beetles. All beetles either have a distinctive maize and blue pattern on their backs, which is the beetle on the right, or they have no pattern, which is the beetle on the left. Of the rare species, which is 0.1% of the beetle population, 2% have no markings and 98% have a pattern on their backs. Of the normal species, which is 99.9% of the beetle population, 95% have no markings and 5% of normal beetles have patterned backs. Given that P of R is the probability that a beetle is rare and P of P is the probability that beetle is patterned, what is the probability of R given P? Let's say that we find a beetle that is patterned. What is the probability that this patterned beetle is rare? Again, we write out the probability using Bayes' theorem. We then plug in the values that we are given in the explanation slides. So the probability of a rare beetle is 0.1%, and the probability that the beetle is patterned, given that they are rare, is 98%. So after we plug in all the values, we then find that the probability of a rare beetle, given that they have a pattern, is actually very low, around 2%. And this makes perfect sense because rare beetles are so uncommon that they are only 0.1% of the entire population. So thank you for watching. I'm Jenny.
And I'm Ben.
And we're part of Group A11 of EECS 203. Feel free to go to the link listed below for more videos like these.